Okay, so section 2, alpha halogenation. I've also done this in class. In this reaction, you treat an enolizable carbonyl compound. So this has to be enolizable, which means it has to have at least one alpha proton. Acetone has 6, but you have to have at least one. And the alpha halogenation product will be that. We'll just stick a bromine, we'll stick a halogen on the alpha carbon using molecular halogen, either Cl2, Br2, I2. Br2 is by far the most common to use here, just like it is in halogenation of an alkene. Okay, so how does this work? Well, remember, the carbonyl compound has a little bit of enol in it. All right, at equilibrium, there's like 1 trillion acetones for every acetone enol. But if you have 10 to the 22nd, third or so molecules, you're going to have a significant amount of the enol. And then this is going to react just like an electron-rich alkene. Okay, and an OH is an electron donor, methyl's a weak donor. So that's going to just do halogenation. Going to get the bromonium ion just like in a halogenation reaction with an alkene. You've got some Br minus sitting here. Okay, and so that Br minus takes the proton, regenerate your ketone, kick out bromide to go up to the product. I turned it around, sorry. Okay, so that's it, that's the reaction. There's a reaction that we talked about in class called a haloform, and that is if we take, let's do this to keep it a little simpler. All right, so if we take a methyl ketone like so, you could make that with a Friedel-Crafts acylation from chapter 18. And if we treat this with, no, that's not right, drawing a problem. All right, if we treat this with, say, iodine and aqueous sodium hydroxide, so now we're under basic conditions. The product we're going to get is the carboxylate and a molecule called iodoform. Okay, iodoform, you've heard of chloroform. Chloroform would be just that structure, but instead of iodines, it would have chlorine. You also can make bromoform or fluoroform. Fluoroform is pretty rare to see, but it's around. So the way this goes is we do alpha halogenation 3 times. So why can we do it 3 times here? And the reason is we have base. So now the mechanism isn't exactly the same. You actually make some enolate. So over here, under basic conditions, right, with just Br2, the reactions, Br2 is a weak Lewis acid. You make HBr in the process, so you run it under acidic conditions. Here we're going to make it enolate. There's a video on making enolates. You should go take a look at it. And then iodine. Okay, so under acidic conditions, we need to make enol, and that enol with an electron withdrawing halogen on it is less reactive. So typically, when you just add molecular halogen, the reaction stops after 1 addition. With base, the pKa here, the pKa of this one is now lower. So this is more acidic, and so if you add base in, you tend to fully halogenate. So if we start with a methyl ketone, we get 3 iodides on it. Okay, now the last step is like a hydrolysis from chapter 20. Okay, so hydroxide adds in, pop the electrons up onto the oxygen, minus OH, Ci3. Now, the O minus can kick OH back out. That probably happens some. It can also kick out Ci3. And this is why I say this is just like a hydrolysis reaction. you get CI3 minus. That's a much stronger base than a carboxylate, and so the acid-base equilibrium favors protonating the CI3 and giving the carboxylate. Okay, so to sum up, alpha halogenation, if you treat a carbonyl compound, aldehyde, ester, well, aldehyde's typically oxidized to carboxylic acid. It's kind of a side thing. But a ketone, and ketones are best. You can do this a little bit with esters, carboxylic acids. There's a cool reaction called the Hell-Vollard-Malinsky reaction. Anyway, basically, you're going to put a halogen on. You're going to replace an alpha proton with a halogen. If you just use molecular halogen, that typically stops at one addition. If you use base, you typically exhaustively halogenate the alpha positions. And if that gets you 3 halogens, if you have a methyl ketone and you get 3 halogens on there, the C halogen 3 anion can be a leaving group in a hydrolysis step. All right.